In the last lecture, we started talking about sinusoidal steady-state analysis, in which you had an RLC circuit driven by voltage and current sources that, rather than being DC sources, are sinusoidal sources. And what we saw is that even in a very simple case, such as a single loop RLC circuit, when you do sinusoidal steady-state analysis in the time domain with differential equations, the mathematics is very unwieldy. We also saw that by using the concept of phasors, in which you model voltage sources, current sources, and voltage and current variables as complex numbers in polar form, you can greatly reduce the complexity of the math and make the problems more doable. Today we're going to take it a step further. We're going to introduce the concept of impedances, which, along with phasors, are going to allow us to treat sinusoidal steady-state circuits with resistors, capacitors, and inductors as if they were DC circuits with just resistors. The only wrinkle is that all of the math is going to be using complex numbers. So let's continue with the lecture today and talk about the concept of impedance. So as I said, phasors themselves give you a nice mathematical shorthand for dealing with sinusoids. But the problem is you still have these differential equations, and that's because for capacitors and inductors, the VI characteristic is a differential integral relationship. For example, in a capacitor, we know that the voltage across the capacitor is 1 over C times the integral of the current through the capacitor. Likewise, we know that for an inductor, the voltage across an inductor is what? It's L times the derivative of the current through the inductor. On the other hand, for a resistor, the relationship was much simpler. We know from Ohm's law that the voltage across a resistor was nothing more than the resistance times the current through the resistor. Wouldn't it be nice if we could have relationships for capacitors and inductors that looked more like the relationship for resistors? As it turns out, we can, and that is using the concept of impedance. It's basically a generalization of resistance that allows us to have a completely algebraic model for the KVL and KCL relationships in a circuit without using differential equations at all. So this is the key term here, is we're going to avoid differential equations completely, at least in the sinusoidal steady state situation. What we're going to see is that the derivative integral VI characteristics that we saw with capacitors and inductors are going to be replaced with algebraic relationships that have complex numbers. And then finally, what we're going to see is that if we use this impedance concept in conjunction with the phasor concept that we already covered, we're going to greatly reduce the mathematical complexity of these problems. One important point here, this doesn't help with transient analysis. The stuff we're looking at now only helps with sinusoidal steady state analysis or AC analysis. So as a suggestion, we sort of hinted at this before, but let's look at it again. Every time we see a capacitor in a circuit, let's replace it with a complex resistance, which actually we're going to call impedance, 1 over j omega c. And I do need to point out that remember that 1 over j is the same as negative j, so 1 over j omega c can also be written as minus j over omega c. In fact, that is the way I prefer to write this impedance of capacitors. Resistors, we're not going to touch. Inductors, wherever we see an inductor, we're going to replace it by a complex resistance, actually an impedance as we're going to see, called j omega L. Then what we're going to do is just do KVL and KCL equations as we normally would. So let's look here first. If you had a DC situation where you had a voltage source Vs, resistors R1, R2, and R3, if you did the KVL, you get minus Vs plus a voltage drop across the first resistor, R1I, plus a voltage drop across the second resistor R2I plus a voltage drop across the third resistor R3I is equal to 0. We get that expression there. Solving for I, and it's Ohm's law, we see that the current is just the voltage across the series resistances divided by the resistances. The idea now is we're going to do the same thing if you have circuits with capacitors and inductors driven by a sinusoid by using what we call impedances. Wherever we see a capacitor, we're going to replace it by 1 over j omega c or minus j over omega c. Wherever we see inductors, we're going to replace it by j omega L. And then, of course, we're going to have our phasor voltages and our phasor current variables. And now when we apply KVL, here, 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 we're going to get minus Vs plus, instead of doing R1 times I, we're going to do this resistance, which is 1 over j omega c times I tilde. And the voltage drop across the resistor is still Ri tilde. And the voltage drop across the inductor is going to be its resistance, or actually impedance now, j omega L times I tilde. And so we end up getting this algebraic equation. And just like on the case on the right, to solve for I, it's basically I is just Vs phasor over the sum of the three individual impedances. 1 over j omega c plus R plus j omega L. And then, of course, 1 over j omega c is minus j over omega c, and we get this expression there. So let's revisit this problem that we did at the beginning of this packet of notes. If you remember, we did this very simple RLC series circuit completely in the time domain, and it took an entire page of math to find out what the current I of t was. We revisited this a few pages later once we understood the phasor concept and saw that it made the math a little bit easier, but we still had differential equations. What we're going to do now is revisit this problem a third time, and now we're going to utilize both phasors and impedances and see how simple this actually is. What we're going to see is that we can convert this circuit to a circuit that looks like a resistive circuit, except we're going to have complex numbers. And then we can solve it just like we would solve a resistive circuit. So the idea here is we want to convert into what we call the phasor domain. To convert into the phasor domain, voltage sources you replace by their phasor equivalent. So Vs phasor is just 10 at an angle of 0 degrees volts. Capacitors and inductors and resistors are now replaced by their impedance equivalents. So for a capacitor, a 0.25 farad capacitor, it gets replaced by minus j over omega c. Omega was 4 radians per second. Capacitance was 1/4 of a farad. It's just going to be minus j ohms. Resistors, you don't do anything to. 3 ohm resistor is still a 3 ohm impedance. The inductor, the 0.5 Henry inductor, it gets replaced by j omega L, which is j times 4 times 1/2, or plus j 2 ohms. So notice, capacitors are always going to have a negative impedance. Inductors are always going to have a positive impedance. And resistors are always going to have a real impedance. Final thing we want to do before we solve this now is, instead of solving for I of t, we're going to solve for I tilde. So we're utilizing two different concepts. The phasor concept applies to both this current variable we're solving for and the voltage source. And the impedance concept applies to the inductor, the capacitor, and technically the resistor, although there's really no change there. Anyway, think of this now as a DC circuit. You have a voltage source, you have 3 resistors, the current is just the voltage, so the current I is just the voltage divided by the sum of the resistances, minus J plus 3 plus J2. Work that out. It's 10 at an angle of 0 volts over 3 plus J1 ohms. You work out the math on your calculator or by hand. You get 3.16 at an angle of minus 18.4 degrees amps. Finally, you do need to convert this back into the time domain, but that's as simple as reading off the magnitude and the phase. So we get the final answer, I of t is 3.16 cosine of 4t minus 18.4 degrees amps. Once again, compare the amount of work in this problem to the first attempt where we had an entire page of trig to get these same two values. All you need to do here, convert the capacitor to its equivalent impedance, convert the inductor to its equivalent impedance, convert the voltage source to its equivalent phasor, and then treat everything like a resistive circuit, use Ohm's law. The only challenge here is the math is complex numbers, but if your calculator can do complex numbers, you can get this answer here very simply. And then as a final step, you undo the phasor to turn it back into a time domain expression. And that in a nutshell is what this phasor impedance concept is all about. Now that we did the simple example, let's talk about impedances in more detail and see where we come up with these two expressions here, and then we'll do additional problems. So here's more detail about impedances. As we said, an impedance is basically a complex resistance. It's a complex number used to represent the VI characteristics for elements or networks in the sinusoidal steady state situation. So once again, impedances are only valid in sinusoidal steady state. It's not a concept you use in transient response. You only use it in sinusoidal steady state response. Notation-wise, we're going to use the letter Z for impedances. So R, we always think about with just resistors, and R resistance is always going to be a real number. Impedances in general are going to have both real components and imaginary components. So just like resistance was voltage over current, R was V over I, that's Ohm's law, impedance is a phasor voltage over a phasor current. And just like you can find the resistance of a single element, or you can find the equivalent resistance of a whole bunch of elements combined together, same thing with impedances. You can find the impedance of just a single element, or you can find the impedance of a whole bunch of elements combined in series, parallel, or some other combination. And so this becomes the general relationship between the voltage across a group of elements and the current through that group of elements. In general, we're going to see that impedance is going to have both a real and an imaginary part. The real part we're going to call the resistance. The imaginary part, we have a new term we call reactance. The units of impedance, resistance, and reactance are all ohms. Way to think about this total impedance, the resistance is going to be due to the resistive part of the circuit, and the reactance, the imaginary part, is going to be due to the capacitive and inductive parts of the circuit. and together we're going to get this total impedance Z, which in general is going to be a complex number. So let's individually look at impedance of specific elements, and then we'll look at the impedance of combined elements. So resistors are the easiest. As we know, in the time domain, we have Ohm's law, V equals IR. So if we convert everything to the phasor domain, voltage in the time domain becomes a voltage phasor in the phasor domain. Current becomes a current phasor. And so we get that VR phasor equals R times IR phasor. So VR over IR, which by definition is impedance, is just R. And so we see that for a resistor, the impedance is the same as the resistance. So what does this mean? Suppose you have 10 ohm resistor. Suppose we know that the current through the 10 ohm resistor is 0.5 cosine of 10t. From Ohm's law, we know that the voltage across a resistor is just the current times the resistance. So the voltage across that resistor is just going to be 0.5 times 10, or 5 cosine of 10t volts. In the phasor domain, 0.5 amps is 0.5 at an angle of 0 degrees, and the voltage is just 5 at an angle of 0 degrees volts. And sure enough, the impedance is just the voltage phasor divided by the current phasor, or just 10 ohms. If we were to plot the voltage and current for a resistor, the current is a cosine, and what we see is the voltage is also going to be a cosine, same frequency, just in this case, a bigger amplitude. And what we see is the voltage and current, or what we call in phase with each other. In other words, they're both maximum at the same points, they're both zeros at the same points, etc. We're going to see for capacitors and inductors, it's a different situation. So now let's look at an inductor. In the time domain, the voltage across the inductor is L times DIL dt. So let's convert this expression here to its phasor equivalent. VL becomes VL phasor. This is just a constant, it comes over there. Remember that differentiation in the time domain is the same as multiplying by j omega in the phasor domain. We saw that in last lecture. So this expression becomes that. And so VL phasor is j omega L times IL phasor. So by definition, ZL, which is the ratio of VL phasor to IL phasor, is just j omega L. And this is where we got this expression from. I should point out that j, of course, is the imaginary number in rectangular form. That same number in polar form is 1 at an angle of 90 degrees. And so ZL, you could, if you wanted to, rewrite it as omega L at an angle of 90 degrees. That would be the polar form of the impedance of an inductor, whereas j omega L is a rectangular form. So let's look at a simple example here. This example, let's have a 10 Henry inductor. And let's have the current through the inductor be 0.5 cosine 10t amps. What's the voltage across the inductor? In the time domain, the voltage across the inductor is L DIL dt. the derivative of cosine is negative sine, and that 10 comes out. So the voltage, we're going to have a 10 because of the frequency and another 10 because of that. And so we're going to get, the voltage is going to be minus 50 sine 10t volts. If we wanted to look at this in the phasor domain, the phasor current is 0.5 at an angle of 0 degrees. The phasor voltage is, we have to think here now, because we have a minus sign and it is a sine. So converting sine to cosine, we have a negative 90 degrees, but then we have another 180 degree difference because of this minus sign here. And so the voltage phasor, V phasor, is going to be 50 at plus 90 degrees volts. Whereas the current phasor, use that designation there, is 0.5 at an angle of 0 degree amps. So here, Z is V over I, 50, 90 degrees over 0.5, 0 degrees, and we get 100 at an angle of 90 degrees. And notice that agrees with that result there. The 100, there's a 10 because the frequency is 10 radians per second in this example, and the L is 10 henries in this example. If we wanted to plot the voltage current relationship in this case, the current is a cosine. So this is I of t. Let's look at the voltage. The voltage is going to be a negative sign. So a couple things we note. When the current is maximum, the voltage is going to be 0. I'm off a little bit there. And when the voltage is maximum, the current is going to be 0. The other thing we see is that the voltage now happens earlier than the current. What we say is that the voltage leads the current, and specifically it's leading it by 90 degrees or a quarter period. So once again, in an inductor, the voltage leads the current by 90 degrees. The other property we see, and this is probably the most important property, is that the magnitude of the voltage is not just a function of the magnitude of the current, it is also a function of the frequency of the current. And that is due to this term here, the fact that there is an omega in that impedance. So what we see is that for small frequencies for a given current, the voltage is going to be smaller, and for larger frequencies, the voltage is going to be larger. Another way to look at it is to think about how much current you have as a function of voltage. For low frequencies, the current is going to be more for a given voltage, or what we call a small impedance. We're not impeding the current flow as much. But for higher frequencies, for a given voltage, the current is going to be less. In other words, we're impeding the current flow more, or we have a large impedance. So what we see is that unlike a resistor in which the voltage current ratio is the same regardless of frequencies. For an inductor, it is frequency dependent, and for that reason, and we saw this much earlier in this semester, the inductor can be thought of as a frequency varying resistance where the resistance, or as we call it, impedance now, is higher the higher your operating frequency is. So let's look at the capacitor now. So once again, in the time domain, we know that the current through the capacitor is equal to C times the derivative of the voltage. So to come up with the impedance, we're going to convert everything to phasor domain. IC tilde then is going to be C, that doesn't change at all. And then the derivative of the voltage in the time domain in the phasor domain becomes j omega times the voltage phasor. Remember, derivative in the time domain means multiplying by j omega in the phasor domain. So ZC, the impedance associated with the capacitor, once again is the voltage phasor divided by the current phasor. It's going to be 1 over j omega c, or negative j over omega c. And likewise, we can express this in polar form as 1 over omega c at an angle of minus 90 degrees, and that's because minus j in rectangular coordinates is 1 at an angle of minus 90 degrees in polar coordinates. So that we see that the voltage current relationship in a capacitor is the exact opposite as that for an inductor. The omega shows up in the denominator as well as the c. So let's look at a quick example here. Now let's have a 10 farad capacitor. And once again, let's start with the current and let the current IC be 0.5 cosine of 10t amps. So what's the voltage across the capacitor here? The voltage is going to be the integral of the current divided by the capacitance. So the voltage in this case, when you integrate the cosine, you're going to get a sine. You're going to divide by the 10. You're also going to divide by another 10 because of the capacitor value. And so the voltage is going to be 0.005 sine 10t volts. So the phasor equivalence, the current is 0.5 at an angle of 0 degree amps. The phasor equivalent of the voltage is 0.005 at an angle of minus 90 degrees volts. Remember, sine, when you convert it to phasor, you have to subtract 90 degrees. And here we see that the impedance of the capacitor is the voltage phasor divided by the current phasor, and we end up getting 1 over 100 at an angle of minus 90 degrees, which once again agrees with that equation. Let's plot this. So the current will make a cosine of a certain frequency. Now in this case, if the current is a cosine, the voltage is going to be a sine. So the voltage might look something like this. Couple things to note. Here's the current. This is the voltage. When the current is maximum, the voltage is going to be 0. And when the voltage is maximum, the current is going to be 0. And what we see in this case, the current waveform peaks earlier than the voltage waveform. So we say the current leads the voltage by 90 degrees, or we say that the voltage lags the current by 90 degrees. So once again, in a capacitor, just like the inductor, the voltage and current are 90 degrees out of phase, but in a capacitor, the voltage lags the current. In an inductor, the voltage leads the current. A little mnemonic to help you remember that is the phrase Eli the Iceman. In an inductor, the voltage, which is also called electromotive force or EMF, so in an inductor, the voltage leads the current, but in a capacitor, the current leads the voltage. So Eli the Iceman is a nice simple way to remember what comes first, the current or the voltage. And of course, in a resistor, the voltage and current are always in phase. The other property, and the more important of the two properties, is the fact that the voltage across the capacitor is a function not only of the current magnitude, but also the current frequency. But here what we see is because this omega is in the denominator, for a given current, the larger the frequency, the smaller the voltage, or the smaller the frequency, the larger the voltage. Another way to look at it is for a given voltage, at low frequencies, you're not going to have as much current. In other words, you're going to impede the current, you're going to have a large impedance. As you increase the frequency for a given voltage, you're going to have more current or less impedance. So we see that a capacitor, just like an inductor, is sort of a frequency-dependent resistance, although impedance is the more proper word to use now. But unlike the inductor, now as frequency goes up, the impedance goes down. So we have the three basic components, resistor, inductor, and capacitor. In a resistor, the impedance is independent of frequency. In an inductor, the impedance is proportional to frequency. And in a capacitor, impedance is proportional to the inverse of frequency. So now that we're done talking about individual capacitors, inductors, and resistors, what happens if you start connecting components together? So maybe you have an inductor plus a capacitor plus another inductor plus a resistor, etc. Well, it turns out that because impedances are just a generalization of resistances, the equations for combining impedances in series and parallel is just like the equations for resistances in series and parallel. So if you have series connected components, and these can be resistors, capacitors, or inductors, the equivalent impedance is just the sum of the individual impedances. But what happens now, because inductors are going to have positive imaginary impedances, capacitors are going to have negative imaginary impedances, and resistors are going to have real impedances, the equivalent is going to be a complex number that consists of both a real part and an imaginary part. So for example, here the Z equivalent would be 4 plus J7 ohms. And once again, the real part we associate with the resistive parts of the circuit, and the imaginary part, or what we call the reactance, we associate with the capacitors and the inductors. Remember, inductors give you a positive impedance, capacitors give you a negative impedance, and both of them have the J in front of them. Likewise, the parallel connection of impedances is just like the parallel connection of resistances. Specifically, the equivalent impedance is a reciprocal of the sum of the reciprocals. Once again, in general, if your components are not all resistors or all not capacitors or not all inductors, your equivalent impedance is going to be a complex number with both a real component and an imaginary component. The real component is due to the resistive parts of the circuit. The imaginary component is due to the inductive or capacitive parts of the circuit. All of the shortcuts that we learned for resistors in parallel also apply for impedances in parallel. For example, if you have two components in parallel, the equivalent impedance you can write as the product over the sum. So if you found shortcuts that work for resistances, they work for impedances as well. The only trick, of course, is that you have complex numbers, so the math is slightly trickier. Let's briefly talk about admittances. So admittance is the generalization of conductance. So if you remember, when a resistor, the conductance is a reciprocal of the resistance. So admittance then is a reciprocal of impedance. So if you take impedance, take its reciprocal, we get admittance, and we use the letter Y to designate admittance. So if impedance is resistance plus J times the reactance, the admittance, you take this, and if you multiply this by R minus JX over R minus JX, so we're multiplying it by 1, but we do that to make the denominator totally real. If you remember, if you take a complex number, multiply it by its conjugate, you get a real number. So the numerator now becomes R minus JX, and the denominator now becomes R squared plus X squared, which is a totally real number. So the real part of this admittance is R over R squared plus X squared. We call that the conductance. So G is R over R squared plus X squared. Likewise, the imaginary part, which is the argument of the J term, is going to be minus X over R squared plus X squared. We're going to call that the susceptance, or the B term. So we have a total of 6 different terms that you have to keep track of. Impedance is the sum of resistance plus reactance, and admittance is the sum of conductance plus susceptance. The units of admittance, conductance, and susceptance are all Siemens, just like the units of impedance, resistance, and reactance are all ohms. An important point to make here is that even though admittance is a reciprocal of impedance, that does not mean that G is a reciprocal of R and B is a reciprocal of X. So G does not equal to 1 over R and B does not equal to 1 over X. And we can illustrate that below. So Z, let's say we have an impedance that's 3, which is the resistive part, plus J4, which is the reactive part. So what's the admittance? To get the admittance, it's going to be 1 over 3 plus J4. Now, we can multiply by 3 minus J4 over 3 minus J4. The idea here is to get the denominator to be totally real. We get 3 minus J4 over 3 plus J4 times 3 minus J4 is 3 squared plus 4 squared, or 25, which you can rewrite as 3/25 minus J 4/25. So the 3/25 is what we call the conductance, and the minus 4/25 is what we call the susceptance. And notice this is not the same as just saying 1/3 plus J 1/4. So it's not that simple to get the conductance and the susceptance. Now, the reality of it is, just like in a resistive case, we really don't use conductances that much. In the sinusoidal steady state case, we really don't use admittances that much. We use impedances much, much more. But it is important to understand the notation here. It is important to understand the wording of admittance, conductance, and susceptance in case that ever comes up in a situation. Continuing on with admittances briefly, just like in conductances, the series and parallel combinations are opposite for resistances. Likewise, for admittances, the series and parallel combinations are opposite for impedances. Specifically, a series connection of admittances is going to be the reciprocal of the sum of the reciprocals of the individual admittances. Likewise, in parallel, you simply add the admittances together. But as I mentioned on the previous page, we typically do not use admittances much at all. So let's finish off this lecture with one example sort of showing the impedance of a circuit that has a combination of resistors, inductors, and capacitors, and using that impedance to find currents. So here we have a voltage source, a sinusoidal voltage source, and it's connected to a capacitor, an inductor, and a couple different resistors as shown in this figure here. And we're asked to determine the equivalent impedance seen by the voltage source at two different frequencies. Remembering, in general, impedance is a function of frequency. If all you had was resistors, that wouldn't be the case. But once you introduce capacitors and inductors into the circuit, the impedance is going to be frequency dependent. And then we're going to use that equivalent impedance to determine the current leaving the voltage source in these two situations. To make things a little simpler, I'm actually going to give a value for this voltage source. We're going to make it a magnitude of 4. And of course, omega is either going to be 1 radian per second or 4 radians per second. So the first thing we want to do probably is draw the phasor equivalent of the circuit. So Vs phasor is going to be 4 at an angle of 0 degrees volts. The capacitor, and I usually like to use blocks here. When we do things in the phasor domain, because we have these three different components, capacitors, inductors, and resistors, and they all have different symbols, but in the phasor domain, they're really all the same thing other than the fact that the impedances are either real or a positive J term or a negative J term. I find it easiest just to use a block for every component. So the capacitor is going to be minus J over omega C, and omega is going to change, so we'll leave that as a variable. C is 0.5 farad, so this becomes minus J2 over omega. The inductor, once again, its impedance is going to be J omega L. L is just 1 Henry, so we'll just make this as J omega. 2 ohm resistor is just 2 ohms. And the 4 ohm resistor is just 4 ohms. And technically these should all have units of ohms. So we're asked to find the equivalent impedance as seen by the voltage source. So we're basically looking to find Z equivalent here. And we're asked to do it for two different frequencies. What I'm going to do is I'm going to find a general expression for Z equivalent first, and then we're going to plug in specific values for omega. So Z equivalent, think of these just as resistors. These two are in parallel, and then that parallel combination is in series with this term and this term. So Z equivalent is going to be J omega in parallel with 2 plus 4 minus J2 over omega. So color coding, this 4 is due to that. This minus J2 over omega is that. And J omega in parallel with 2 is that. So if you work out the math, two things in parallel is the product over the sum. So that becomes J2 omega over 2 plus J omega plus 4 minus J2 over omega. First term, let's multiply it by its complex conjugate to get a real denominator. We now get J2 omega times minus J omega. J squared is -1. That cancels with that minus. We get 2 omega squared plus J 4 omega all over the real part squared, which is 4 plus the omega squared, 4 plus omega squared, plus 4 minus J2 over omega. Let's combine the real parts together. So what's real? You get this over that, and that is the real part. The imaginary part is this over this plus that part. So that equals 4 plus 2 omega squared over 4 plus omega squared plus J times what? 4 omega over 4 plus omega squared minus 2 over omega. So this becomes our R, and this term in parentheses becomes our X. So this is our general expression for the impedance, and notice it is a function of frequency, because although the resistor doesn't change for different frequencies, the capacitor and the inductor do. Okay, let's look at the two specific situations now. When our frequency of operation is 1 radian per second, we get Z equivalent from the previous page. Wherever we see omega, we're going to replace it by 1. We get 4 plus 2 times 1 squared over 4 plus 1 squared plus J times 4 times 1 over 4 plus 1 squared minus 2 over 1. You work out the math, you get 22 fifths minus J 6 fifths of an ohm, which equals to 4.4 minus J 1.2 ohms. So if you think of what we're trying to solve for, the equivalent impedance is now 4.4 minus J 1.2 ohms. The voltage source was 4 at an angle of 0 volts, and we're trying to solve for this current I. So from Ohm's law, I is 4 at an angle of 0 volts divided by 4.4 minus J 1.2 ohms. If you have a calculator that can handle complex numbers, you can do this directly. Otherwise, you need to convert the denominator to polar form because it's much easier to divide complex numbers when they are in polar form. That becomes 4.56 at an angle of minus 15.25 degrees. 4 divided by 4.56 is 0.877. 0 degrees minus negative 15.25 degrees is plus 15.25 degrees. That's going to be amps. So the current in the time domain is 0.877 times cosine. Frequency of operation is 1 radian per second, so it's 1t plus 15.25 degrees amps. So notice at this operating frequency, the current is actually going to lead the voltage. Another way to think about it is if you look at the equivalent impedance, notice the imaginary component is negative. That means that the capacitor has a bigger effect than the inductor because it tends to cause the current to lead the voltage. So let's redo it for a frequency of 4 radians per second. So once again, we're now going to plug omega equal 4 into the equation from 2 pages ago. To get Z equivalent is 4 plus 2 times 4 squared over 4 plus 4 squared plus J 4 times 4 over 4 plus 4 squared minus 2 over 4. You work that out. You get 28/5 plus J 3/10 ohms, or 5.6 plus J 0.3 ohms. So if you wanted to find the current, you now use Ohm's law again. This impedance is 5.6 plus J 0.3 ohms. This current I tilde is what? It's Vs tilde divided by the impedance. So I tilde is 4 at an angle of 0 volts divided by 5.6 plus J 0.3 ohms, which you can either do on your calculator directly if it can handle complex numbers, or if it can't, you need to convert 5.6 plus J 0.3 to its polar equivalent. And then you divide the magnitudes, subtract the angles. 4 divided by 5.61 is 0.713. 0 degrees minus 3.066 degrees is negative 3.066 degrees. And this is going to be amps. Finally, convert it back to the time domain. The current now is going to be 0.713 cosine. Now it's 4t, because we're operating at 4 radians per second, minus 3.066 degrees amps. What we notice here is that the current is going to lag the voltage by a little bit. And this makes sense because the equivalent impedance has a positive J component. In other words, at a frequency of 4 radians per second, the inductor plays a bigger part than the capacitor, and so this is what we call an inductive load. Inductive load happens when the imaginary part is positive. A capacitive load happens when the imaginary part is negative. But notice there is a real part too, and that is because there are some resistors present in this circuit. We will continue the topic of impedances next class with some more examples, and then we'll see how we could use the impedance and phasor concept to solve all kinds of problems in sinusoidal steady state. Have a good day.